Hello, everyone, and welcome back to the Cisco Optics podcast, where we talk about optics for networking. What are the industry's technical experts in pluggable optics thinking about today? What are the technical boundaries that the smartest minds are pushing past to make the next generation of high-speed optics? If you're wondering about this, we have just the person for you. This is episode 8, where we continue a conversation with my esteemed colleague, Mark Noel. Dr. Noel is a Cisco fellow, and for good reason. In my 8.5 years at Cisco, I've known him to be a highly respected and influential leader not only at Cisco, but the entire optics industry. In this final part of our 4-part conversation, we continue talking about thermal considerations, which he's been thinking and writing about lately. We also discuss a useful white paper on the QSP-DD website, which provides detailed design guidelines. Mark Noel is a Cisco fellow in Cisco's Optics and Optical Systems group. His focus is on next-generation interconnect technology innovation to meet Cisco's needs. Mark is also active within the industry standards and forums and has chaired multiple IEEE 802.3 Ethernet projects. He represents Cisco on various industry alliances and consortiums. Mark also chairs a number of industry multi-source agreement groups, focusing on next-generation optical module form factors such as QSP-DD and QSP-DD 800, and optical interface signaling technology like the 100G Lambda MSA. What has Mark not done? If you haven't already, please subscribe to this podcast. It may show up as the Cisco Podcast Network, which has other great podcast series as well. Check out our blog at blogs.cisco.com and search on hashtag Cisco Optics blog, all one word, no hyphen and no spaces. For our YouTube playlist, go to youtube.com and search on Cisco Optics. And for product information, go to cisco.com/go/optics. And now, join me as I talk with Mark Noel. When you were driving the 400 gig QSP-DD MSA, you had to think about the mechanical design a lot, right? And the thermal consequences. How did you take into account all the various system level variability, right? Because there are lots of different routers and switches out there. They don't all blow the air the same way, the same direction, or maybe the same rate. And then even then, like when they get deployed, I don't know, are there different temperature standards at different facilities in terms of the air temperature, like ambient?
There are, and that is a problem. And it's a challenge. So the thing with you create this form factor, and that's great that everyone builds the same form factor, and then as a system designer we're able to go and customize around that, figure out how are we going to go put as many as we want and how are we going to cool them. And then we also have to factor into that what is the operating environment that a customer may deploy it. And so you're correct that it is very different, and service providers have very well laid out environmental requirements, where they may put these things in different altitudes, and what the ambient temperature in the room might be, and where there's a hot aisle and where there's a cold aisle and things like that. The data centers, the web scale data centers, were solving this problem in a much bigger problem set, and so there's a lot more uniformity there. But I think they've recognized that the requirements in terms of the ambient temperature that we run our equipment is more controlled and more reasonable within the data centers than some of the service provider requirements that used to exist. So I think as an industry, it's kind of becoming a bit more normalized now. But we've seen we're typically designing for a lower ambient temperature than we used to.
What is the reason for, when you say it's becoming more normalized, do you mean that like service providers and data center people are coming together now and realizing they need to unify?
I think it's different equipment in different places, right? So where you're putting in the really high density where thermals around optics is such a problem tend to be the big facilities now. And so there things are a bit more environmentally controlled. And sort of the problem the service provider operators have is they're just geographically diverse. They just have to put equipment where people are in cities or in rural areas. And so they maybe have less control over the temperatures in some of those buildings. Or where they're, if you're in Colorado, it's at a different altitude than if you're in San Francisco. But typically they're not maybe putting in the massively high density equipment in the same quantity that a web scale data center would have. So it's, there's different equipment doing different things. So, it allows, as a system designer, we can build that equipment to accommodate those.
I see.
Yeah. So the bigger challenge is really when we're trying to cram it all in together and get it just, the high density stuff for the web scale. So that's where most of the attention has been.
So what's the result of all this attention? What's the state of the art today in terms of cooling pluggable optics?
Well, as I mentioned, it's there's been huge innovation around what we do around these optical modules. Actually, the QSFP I'll just put a shout out to the MSA. We just published a white paper. So there's a QSFP double density MSA. I can't remember the QSFP-dd.com or something. There's the thermal white paper. Anyone really wants to go in and get more detail than they ever wanted. There's a good white paper that we just published with a lot of these details, but
I can put it in the notes of the podcast.
Okay, no, that'd be great. And we kind of broke it down into two areas: is what can you do inside the module, and then there's what can you do outside the module. And I think what we realized, because we were running into a lot of challenges. Not challenges. We were seeing a lot of variability coming from the module designers, and so different module architectures were performing better than others, and so a lot of it came down to understanding what, from a thermal perspective, what made things operate better, and it really is about ensuring you've got a very low. I say low impedance, which means that the flow of thermal energy has the least resistance, right? So how can I get the heat that's being generated from my laser or from my DSP chip? How can I get it to the top surface of my module as efficiently as possible? And it's just things like putting in thermal interface materials in your module, or just worrying about things like the thickness of the case material. The thinner you make something, the harder it is for heat to flow through it. And so there's a whole bunch of techniques that you can go do to increase your ability to get the heat to the surface of the module. And then we also innovated a little bit where we didn't want to attach a heatsink to the module inside because we had to have that backwards compatibility. But we found that if we just actually put a heatsink on the nose of the module that sits on the outside, the air does actually go through that. Because it's getting pulled into the equipment, the air is getting pulled in. If it goes through the nose heatsink, that allows some dissipation of the heat before the air even comes inside the equipment.
Sorry, can you back up a second and just kind of describe? We don't have visuals at our disposal, but can you maybe describe in words like the shape of the module, the nose that you mentioned?
Yeah. So I mean, an optical module is just really a little rectangular square box, right? And it's a little metal square box. At one end, it's got an electrical connector, which is really just the edge of the card, and that plugs into the back of the inside the system. And then at the front of the module, you have that sticks out of the faceplate that's the nose. And that's where the optical connector, that's where you attach your patch cord.
Okay.
And the amount of
earlier modules like SFP Plus, there really wasn't a nose. That you plug it into the port and it kind of disappears into the port, right? I mean, there's a little bit of a nose.
Well, yeah, there has to be something, because you have to be able to get your fingers in to put the patch cord in. And the QSFP is the same. And the problem I was describing at the beginning about how do we fit all this into a 400 gig module, all of the optical module companies came back and said, hey, that's not a lot of space in there for all of this new technology. Can we push that nose? Can we extend that nose out a little bit further to give us a bit more space inside the module? And so as an industry, we kind of looked at that and said, yeah, that makes a lot of sense. And so and we call that within the QSFP, we call that type 1, which is the old way, the shorter one, and type 2, which is the longer nose. And so modules that don't need the space, they don't have to use that extension. It doesn't matter. It doesn't affect the interoperability at all. It's still the same port in the equipment. Right? And what I was describing, so that nose is now sticking out of the module, what we found is if you have a very, very high power module, you can actually go and attach a heatsink to that. And it just comes as part of the module, so it's no different. But just by putting a
heatsink, meaning the fins, or
heatsink is just fins. Yeah, when I talk about a heatsink, it's a piece of metal that's shaped so it has fins that the air goes by, and you're just trying to increase the surface area so that heat will transfer from metal to air, and the more metal there is, the more it'll transfer, the more surface area there is.
And if it's a front to back airflow switch or router, then the router takes care of drawing the air from the ambient environment through the fins of the nose.
Most equipment these days now is all built so that it's fans at the back of the equipment, and it's just sucking the air from the front. So everything comes in through the faceplate of the equipment. So we have these fans sucking, it creates a negative pressure, and that just draws the air in. And it pulls it through the nose as well. If there's a heat sink on the nose, it just pulls the air through that as well. So you're already transferring heat off the module before it even comes into the equipment.
Is that direction required? Or like say a 20 watt module, or?
I think it depends on the density. I think a lot of equipment, especially on the server side, the fans are reversible. So you can either have them drawing, air into the faceplate or pushing air out of the faceplate. And it really, it depends on how they configure. And some customers would like all their cables hidden and in the back. So they just turn the equipment around and then turn the fan around accordingly. I'm not, most of the equipment that I am familiar with for these higher powers is all pulling it into the faceplate.
Yeah, I mean, if at 400 gig, if the main heat sources are at the front faceplate, what reason would there be not to have front backflow? You would think that would be the natural design.
Yes, yeah, and for the high density boxes, I'm being hesitant because I'm sure there's a use case where you would want to have the optics at the back and have the cabling coming out of the back of the equipment, and you would turn you change the fan directions and push it out the front. But I don't think it would be on equipment where you'd maybe have 32 ports. I'm sure someone will prove me wrong, but it's definitely easier on the cooling of the optics to have it being drawn in, having the cold air from outside hitting the optics first, because we then have to cool whatever's behind the optics, and we generally have a very high power ASIC back there as well. So, I mean, the thermal design of the systems is very complex, figuring out how to deal with all this preheated air and keep your ASIC.
And And then you
cool.
also have to make sure that it's like within the aisles of your data center or something, right? You make sure that it's not a hot aisle that you're drawing in.
Yeah, so the network operators they'll lay out their equipment a certain way, and typically they would either have they would not have you pulling any air into your equipment which has been preheated by some other equipment. So it could be back to back. So there you got this hot aisle, cold aisle thing, and there's a lot of innovation at the data center environmental level of how they do that and how they build the buildings and keep them cool.
Hey, getting back to that white paper that's on the MSA website,
right?
Is that something that I guess people in the industry can use as sort of like a design guide?
Yeah, that was the intention. That was the intention, because there's a lot of noise in the system around, can these things be cooled, and what we realized, from a Cisco point of view, and when we went and talked to a bunch of other companies, is we've got a massive amount of experience on solving these issues, and that's why we were fairly confident that we could do the QSFP-DD. But we need everyone to be able to do it in order to have interoperability and have create that economies of scale.
Right. And so it's a standard, and you're trying to get everybody, all the players.
Exactly, right. And so right. This white paper, I think it was about 5 or 6 companies all got together, and there were some module companies and connector companies and system companies all coming together and comparing notes on how would we explain all this, and using our various different expertises. And so it was really to just kind of push some knowledge out into the industry that, how you would approach doing these things.
Okay.
We can't control who's going to be building the equipment. And,
So I think you described it to an extent. Can you just sort of recap what's in the white paper? What does it cover?
Well, it covers 2 things. It covers what's, some of the, and it's really just meant to be, here are the 3 or 4 different things you can go do, and it gives you some ideas to what works there. So we concentrated the white paper on how to optimize things within the module. And that was the first bit we talked about. And we didn't talk about the second part, which is really what can you do at a system level to maximize how do you cool these modules. So you've got them, and you hope the module designer has done a good design to get the heat to the surface of the module. And then your job as a system designer is to get that heat away and keep that case temperature down. And so a lot of the innovation I was talking about is captured in this white paper, but it's all about how do you customize heat sinks within these cages? How do you customize the cage design itself? So before, as I said, it was like these kind of coffins that you would slide these modules into, and they would just kind of little ovens and heat up. Now we've got these cages where they're really opened up, so the air flows through them. We embed heat sinks inside the cages, because there's often within a cage there's what we call a stacked cage. So there's 2 of them. There's an upper and a lower port, and that lower port is getting cooked because it's got something above it that's generating heat, and there's no air going through it. So how do you open up the cage so the air flows through the cage? You put heat sinks within the cage and on top of the cage, and then how do you actually put these in your equipment? How do you space them? You can maybe turn them sideways. There's a whole bunch of different techniques that you can go and do, and the beauty that we have come to appreciate more is that QSFP double density design, which we thought was a drawback because it was small and it was flat topped, turns out to be a boon because it's flat topped. as a system designer or a cage designer, we have almost an infinite amount of flexibility on what we do there. Right? So you just plug that thing in, and the system designer working with a cage designer, connector designer will have gone and done a bunch of things in their design to guarantee that module stays cool. And that's where all the innovation is. And that the mere fact that you have a flat top has given us this flexibility to go and make all these optimizations to allow us to get to these 25 watts. And it's very, very interesting.
Yeah. And it sounds like this white paper is going to be a really valuable resource as 400 gig, continues to get deployed and designed into systems.
Yeah, absolutely. And the reason actually it got put together, this wasn't our first white paper that the MSA put out, but we're now looking ahead and looking at 800 gig, and all of the same challenges and motivations exist, where it'd be really nice to stay in the same form factor, and oh my gosh, we're going twice as fast. How do we fit all that in, and how do we cool it all? And so there was again sort of like, hey, is this going to be possible? And the conclusion we came to is absolutely, right? We looked at all what we think is the maximum power we're going to see for an 800 gig optics, and again, it's that long haul coherent optics, and so we're saying that's, we use 25 watts as that target, and we went through the exercise of proving out through experiment and through simulation that it was perfectly feasible to cool that. And our own work internally, I think 25 isn't the max at all. But okay. It's just interesting. I sometimes step back and say, wow, this was a 3.5 watt device, and now we're doing so much more.
You squeezed out so much from this tiny little rectangular box.
Yeah, it's very interesting.
So what is the state of this 800 gig MSA at this point?
Well, 800 gig is so the MSA is the QSFP DD MSA. Actually, a second MSA got generated called QSFP DD 800.
It's got its own website, right?
It's got its own website,
which I can find it and put it in the notes.
And there's a spec there, but I would, depending on when anyone listens to this, what I would do is just revert them back to the QSFP DD website, because what we did is we took that 800 gig spec and we handed it back to the QSFP DD MSA, and they've incorporated that into their spec. So there's just going to be one spec. It's going to have the 400 gig module. It's going to have the 800 gig module. It will also have what many people would know of as QSFP 112. So that's a 400 gig module with only the four channels on the electrical side. So all of those will be in, and so it's March when we're talking now, and I would say in the next 4 to 6 weeks that's going to be published.
Okay. I think this podcast will get published starting probably around that time, actually.
So yeah, hopefully it'll all be out there. And to, so the challenges with 800 gig were the thermals, which as we've been talking about, I don't think are a concern. And on the signal integrity, how do you get this 100 gig electrical signal into this connector? And that's what the MSA spec defines. It's some tweaking and optimizations to the connector and the pads, and all the signal integrity looks really good. And so we're going to be seeing, in the not too distant future, we're going to be seeing 800 gig modules. Most people are going to use them as in a breakout configuration. So it'll really be 2 400 gig interfaces or 8 100 gig interfaces. But the module itself has an 800 gigabit capacity with it.
Okay. So the 800 gig. Sorry, did you say they're 100 gig channels? Or 50 gig channels?
No, so the 800 gig module has 8 100 gig electrical channels going in, and then coming out, it'll be, depending on which module you use, it'll probably be 2 400 gigabit Ethernet ports, or it'll be 8 100 gigabit Ethernet ports.
Okay, but in breakout mode, it can connect to these single lambda 100 gig.
Yes, yeah, it would be
the other end.
Absolutely, yeah. And the IEEE is starting its work now on 800 gigabit Ethernet, and that will take its time to work itself out. But the module's already there. So when we do actually have true 800 gigabit Ethernet optics.
Cool. Mark, this has been really educational and fascinating. That was the fourth and final part of my conversation with Mark Noel. Make sure to check out the notes section for links to other resources such as the white paper on the QSAP-DD website that Mark mentioned. Subscribe to this podcast, and we'd really appreciate you helping to get the word out. Share this with friends and colleagues that come to mind when you think of network technology and optics. And leave a review on Apple Podcast, formerly known as iTunes. We're also on all the other major podcast platforms. You may see the Cisco Podcast Network come up when you search on Cisco Optics Podcast. That's just where we live, and you can find other great podcasts there too. Also, check out the Cisco Optics blog at blogs.cisco.com and search on hashtag Cisco Optics blog with no spaces and no hyphens in there. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you for listening. This is Pat Chow, Product Manager at Cisco Optics. That concludes my conversation with Mark Noel. Until next time.